Okay, 6.1, slope fields and Euler's method. We're not really going to do either one of those things today, but we are going to talk about differential equations and solving them. So a differential equation, differential means derivative, yes? So it has a derivative in there. So y equals y prime x plus b. Okay, so should be similar to what in your brain? Y equals what? Mx plus b. And what is m? Slope. It is slope, but this is linear, yes? And what is a derivative? We've talked about over and over. It is a slope function, right? So it's a non-constant. So basically, it can't be a linear line, so it can't be y equals mx plus b, but it is a line that fits a function, okay? So a general solution, all we do is we set it equal to 0. So we subtracted the y prime x over, and then it equals to 0. Good. Okay, so it's verify the solution. Is the function a solution of the differential equation y prime minus y equals 0? So what we need to do is we need y double prime and y, because that's what it says in there, correct? Like right here it says y double prime minus y. So we already know y equals sine of x, so we need to find the second derivative. So the first, I need to write in a different color. It doesn't stand out, does it? So y prime would be what? Cosine of x. And y double prime would be negative sine. So we're going to plug it now into that formula. So y double prime, so negative sine of x minus sine of x. Does that equal 0? Nope, it equals negative 2 sine of x, which does not equal 0. So, is it a solution? No. Nope. So whatever they say the differential equation is, that's what you need to have.
And you're plugging them in.
Yeah. So if it was y prime minus y, you just need to find the first derivative. If it was y triple prime, so the third derivative. Okay. So first derivative is what's the first derivative of 4 minus e to the negative x? How about negative 4 e to the negative x? Because the negative. Okay, so what's y double prime then?
Wouldn't it just be 4?
Yep, because it'd be 2 negatives, wouldn't it? So first derivative is negative 4e to the negative x, and second derivative is 4e to the negative x. So 4e to the negative x minus 4e to the negative x. Does that equal 0? So 0 equals 0, so it is a solution. Okay, so C, the next one, I have y equals c e to the x. C is a constant, any random constant. It doesn't matter what it is, right? It's just a constant. So what's the first derivative of that? C e to the x. And second derivative, I forgot my first derivative sign. It'd be c e to the x. So we're going to have c e to the x minus c e to the x equals 0. So is it a solution?
Yes.
Yes. For any value of c, it is a solution. That was a very long siren. And I love how they don't blow all year until the last 2 weeks. Somebody told me they blow every day or every Tuesday. I'm like, no, they don't. Like last Tuesday and this Tuesday.
Yeah.
I wonder if it's just because of the time of the year since it's spring and tornado season. I don't know.
I know it used to go off every Tuesday. I know in the summer it goes off a lot.
Okay. So, back here. Let me go back here. I said it works for any C, yes?
Yeah.
So we can change that C. Changing that C would make the graph look. See how that, if I have y equals C over x, it's a general solution, right? We don't know what C is. But if I change the C's, you see the different graphs I get. Do they all basically have the same shape? It's just different quadrants or different slopes, right? Okay. The curve it would be x, y prime plus y equals 0. So that's the solution curve. And if I change those c's to different numbers, these would be the different graphs I would get. Now, this is a rational function, so I'm mirrored. So I'd get this one and what? This one. I get both of those pieces. So when we do slope fields, that's what we're doing. We're going to construct something that would account for all the different C's that would happen. Okay? We are going to make very small slope fields by hand because slope fields are like you're graphing the slopes. So can you imagine graphing the slope of 1/2 to 1 to 3/4? Would those be really hard to graph? They're like little slanted lines. Those would be horrible to graph, wouldn't they? So I'm still trying to find a good way to make them, but I haven't accomplished that. Okay, for the differential equation x y prime minus 3y equals 0, verify y equals c x cubed is the solution. So verify, so that means it is, yes? Yes? And find the particular solution determined by the initial condition of y equals 2 and x equals negative 3. So how are we going to verify it? Plug it in, right? So we have y equals cx cubed. So y prime would be?
3c.
It'd be 3cx squared. Now, just a second though. Well, 3 times c is still just... Okay, they're going to distinguish the difference between them. Okay, we'll leave it then.
So now do we just plug them?
Now we just plug them in to the differential equation. So we have x and y prime is...
Is our x going to be the negative 3?
No, it's just x and y prime is 3cx squared. Minus 3, and what's y? Cx cubed. Well, I get 3cx cubed minus 3cx cubed, which is what? 0? Okay. Now it wants us to put in, we need to figure out what c is, don't we?
Yeah.
Yes. So we have this equation. I have y equals cx cubed. Well, what they tell me y was? 2. So 2 equals c. And what they tell me x was? So negative 3 cubed. So that'd be negative 27, right? So c is going to equal negative 2 over 27. So since this is c, then I plug it back into the original equation. So I get y equals negative 2x cubed over 27. So now I have a particular solution. So this is a particular, and is that what we did when we found particular solutions before?
Yeah.
Because the particular solution gets rid of that c. Now we've done that with integrals, where it's the same process here. Okay, so we're not doing slope fields today. We're just doing this today.